Physics, atoms, equation. Okie dokie. So, this is what we're going to have a look at. Write this down, please. Do you know this person? Yep, you know him? That's the one? That's the one? Yes. I'm sure his name is the same as Chinese. Yeah. Oh, is it?
Well, that's English.
Yeah. How would you say his name in Chinese? Almost the same. Say it for me.
Einstein.
Almost the same. Yeah. So you know him. You know him and you know him. Do you know this person?
Yes.
You do know him. Good. Okay. And you actually know the equation I'm talking about. So we're going to have a look at Einstein's equation, basically, and some other things too, but mostly that. Okay. So let's have a look at the following nuclear reaction equation. I have here one hydrogen, hydrogen 1, and lithium 7, and they come together and they make two, oh sorry, that should say helium, so that's a helium. Now, how many protons do I have here? 4. And how many do I have here? 4. And how many nucleon do I have? Protons and neutrons? 8. And here? 8. So it seems balanced. Yep. So is it balanced? Well, it seems to be. Seems to be. Let's have a look at the masses though. So the mass of hydrogen 1 is 1.007 AMUs. Remember AMU? It's something like 10 to the minus 27 kilograms, something like this. The mass of lithium 7 is about 7 again. And the mass, again, I'm sorry, that should say helium, it's 2 protons, is about 4. It's almost. So can you add these together and get me the mass here? Add them together. 8.023 AMU. Now the mass of helium is 4.002. And how many of these do I have? 2. So what's the mass on the right? 4. Now, you just saw there that who said the mass on the left is 8.0023 and the mass on the right is 8.004. So they're not the same. No, they're not the same. The mass is less on the right. If you calculate this mass, it's smaller than these two masses put together. And that's a little bit strange if you think about it. You know, if I have mass 1, mass 2, and I put them together, the mass we think should still be 1 plus 2. Why should it be different? Yeah? Yes. Oh, well, you know the answer already. Yeah. So we'll get to it. So what's going on? Mass does not just disappear, or can it? So, let's have a look at this again. We're wondering if there's something missing here on the right. Okay, we're not sure. So what I want you to do is just make notes of this example here and its masses, but please change this to helium, and this should be helium, and this should be helium. Now you don't need to write my words here, you can write whatever you want, but I think this here, with these 3, is important. And then here again, now with the question mark, my right or put down. Okay, did you write that down? Yeah, you're still writing. Yeah? Yeah? Okay. So, this experiment is actually not too difficult to do. All you need is some lithium, and then here, one hydrogen atom, what makes one hydrogen atom? One proton? Yeah, in fact that's it, one proton. So, what charge is a proton?
Plus one.
Yeah, it's plus one charge, isn't it? So, if you put it in an electric field, if I put my proton here, my H1, in an electric field, what will happen to it? It'll move, yeah. It'll move by the force F equals QE. You remember this. So what happens to this proton here? It will move. It will accelerate. So you just put a little hole here in the plate, and the proton will fire through. Like in chemistry, like the electron gun, like a proton gun, it fires a proton. Then what happens here is the proton hits the lithium, and then off comes here a helium-42, and here comes a helium-42. So what happens is you have one hydrogen, and it hits a lithium-7,3, isn't it? Yeah. And then that becomes a helium plus a helium. Or in other words, it becomes 2. See, this is why I don't like putting the numbers on the left. It becomes this. Okay, so you can see the experiment is not so difficult to do. And if I go back here, this was done by Cockcroft and Walton. They did this experiment in 1932. Now, they didn't just decide to do this experiment one day. What they were trying to do was to prove a formula that Einstein had. I think Einstein had this formula in 1910. They did this experiment in 1932, something like this. So Einstein had this formula. Einstein predicted that when atoms combine in a nuclear reaction, with some of the initial mass appearing to be lost, it was in fact not lost, but rather converted into energy. So that missing mass, the mass that we thought was lost, it wasn't actually lost, it was converted into energy. So that can basically be summed up into this formula, that Einstein said that the energy you have is equal to the mass that you lose multiply c squared. Or, as Abraham said earlier, as you more normally see it, is often just written like this.
I have a question.
Yes?
Why is not 1/2 and 6
so it looks like kinetic energy. It's a good question. The proof of this formula is a little bit too difficult for the class. I would like to do the proof with you, but I can't. But it's not like kinetic energy, it's a difference to kinetic energy. I know it looks like kinetic energy because of the m and the speed here. I'm sorry, the proof is a little too difficult. Just a little too difficult. It uses lots of integration in the proof. I'll see if I can find a simpler proof at home. Maybe I can. Anyway, this is his formula. So you have this. And have you seen this formula before? Have you seen this before? No. Have you seen this before? Yeah. Okay. So what we'll do now is we'll go back to the example of what Walton did. Again, I'm sorry, that should say helium. And what we'd like to know is how much energy is made. So firstly, again, that should say helium, this is quite terrible. What I'd like you to do is calculate the mass before, calculate the mass afterwards, and tell me what the difference is. So I'll write it down here. So the mass before the reaction is equal to 1.007 and then plus. Are you giving me the final answer, are you?
No, just it.
Oh, okay, what is the thanks? Yeah, go ahead. 7.016. So that equals 8.024 AMU. What? Thank you. The mass after equals 2 times 4.002. So that equals 8.004. So the lost mass is equal to 0.017. Sorry, 9. Isn't this it? Okay. Now let me get this in kilograms. I think you have this constant on your calculator, the AMU. Maybe it's written as U or AMU. Is it there anywhere? That's atmosphere. I mean, it's going to be roughly the same as mass of a proton, but not exactly it. No, AMU. Oh, there's a U there. Yeah, that's the one. 17. Constant 17. Yeah. Equals? Yeah, that's the one. So 1.66 times 10 to the minus 27 and multiplied by that number. Tell me what you get. Oh, it should be very small. Yes, that's right. It should be. Okay, what did you get?
I get 3.155 times 10 to the minus 29
kilograms. Okay. Yeah. So Einstein said that the amount of energy that you make here will equal to m multiply c squared. And c is the speed of light, of course, which we remember as being 3 times 10 to the 8th, isn't it? Now tell me what you get.
2.8 to the power 10 to the minus
2.8 times
10 to the
minus 12 joules. Now you might think that's still quite small, but in fact it is really, really big when you compare it to, for example, the mass. You know? It's a much bigger number, like a million, or how many times? 17 zeros. 17 times, 10 to the 17 times bigger. It's actually a big number. compared to the mass. Okay. Can I go back to the slides? Yep, okay. So the mass of a proton is this, and the mass of a neutron is this, and the mass of 2 protons and 2 neutrons. Okay, so think about this. I have a proton, I have a neutron. There's the mass of a proton, there's the mass of a neutron. Now if I put 2 protons and 2 neutrons together, what do I have? Helium, yeah. And you would think that the mass of helium should be the same as the mass of 2 protons and 2 neutrons, because that's what helium is. It's 2 protons and 2 neutrons. But in fact, when you put the 4 pieces together, the mass is not 4.03 AMU. In fact, the mass is less than that. The mass is only 4.002. So again, we put our proton, proton, neutron, neutron, we click them together, and the mass is now smaller. This is also strange. So 0.02928 AMU is missing. This is known as the mass defect, is how much mass is missing. So I think this is a good example to write down. In the exam, you know, they will use words like mass defect. So in fact, I would like you to write this down. If you wanted to say, you could say the mass of 2 protons and 2 neutrons, and maybe here you could say that's helium. You got that? Yeah? Okay. So we have a definition now. So first let me just go through it. The binding energy of an atom is the energy required to hold the nucleus together. This energy E is equal to mc squared again, where m is the mass defect. That is the apparent loss in mass when the protons and neutrons are combined together. So in other words, that mass did not disappear. The mass was changed into energy. The energy needed to keep the nucleus together. So this is called binding energy. It's a little bit like in chemistry, you know, you have bonds that keep structures together, like crystals and things like this. Binding energy keeps the nucleus together. So it's a similar idea. It's like a bonding, except it's more basic. It's inside the nucleus between the proton and the neutron. Whereas I think in chemistry your chemical bonds are just like your valence bonds with the electrons, yeah, just like this. Whereas this bonding is in the nucleus. You got that? Yeah? Okay. This is also the energy required to separate the nucleus. Now you don't need to write that down, that's just an extra point. But if you said to me, okay, I have protons and neutrons together and they make helium, how much energy do I need to separate the protons back to one proton and one proton? That's also equal to the binding energy. It's the energy you need to break this bond as well. Yeah. Okay. Let's have a look at an example. What is the binding energy? Now I have it right. Helium 4. The mass of hydrogen is this. The mass no, it's wrong again. The mass of helium is this. And the that's all I need to know actually. Oh, but I also need to know the mass of a neutron. Did you write that down? Do you have that mass of neutron? You wrote this down, yeah? Yeah, okay, good. Let's have a look at an example then. Okay. Alright, so I have proton, neutron, and neutron. What's the mass here? I think I actually worked it out in my paragraph.
Yes, what on
3182 AMU. And then what I do is I click them together, and now what do I have? I have my helium 4. And what's the mass of helium 4? I give this to you. It's 4.004, is it?
Yes. No,
002. Okay. So you can see that there is a difference here. This is called the mass defect, or just the M if you want. And how much is it here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if I subtract, I have 2, 8, 20. Is this right?
Yeah.
Are you sure? Don't trust me. Is it right? Yes. Okay. So on your calculator, can you give this to me in kilograms, please, using your constant U? Go on, Neil. Don't just sit there. 10 minus
29.
29. Yeah. Okay. So now we can calculate the binding energy. It's equal to mc squared, which is 4.9 times 10 to the minus 29 times 3 times 10 to the 8, which equals
8 squared.
huh?
Yes, squared.
Oh, my goodness, thank you. Oh, did we forgot to square in the last one? Oh, we did square it. Good job. Square here.
1 to 4 times 10 to the minus.
What is this? 4 point...
4, 5, 6.
4, 4, 5, 6.
4, 5, 6.
Yeah, go on.
Times 22 minus 12.
Joules. Yeah, did I? Oh, that's terrible, Stephen. There should be a square there. Okay, so this is the energy. So you can think about it this way. If you want to break these bonds, you would need to use this much energy to break the bonds. That's one way of thinking about it. Or another way to think about it is if you want to put these together, you would need this much energy. So this is the energy of the bond. I don't know if you do this in chemistry. Do you do this anything like this in chemistry? The energy required to break the bonds?
Yes.
You did, yeah? And what unit do you use?
Joules.
Use joules? Yep. So this is how much energy you need to break the bond between the protons and the neutrons here. What's the name of the force that keeps these together?
Force.
Yep. Which one?
Molecular force.
No.
Interaction force.
No. Strong nuclear force. Remember this?
I'm thinking about it.
Yeah, that's okay. That's okay. So this is how much energy you need to keep the bonds together, the protons and the neutrons together. So this is called the binding energy. Let me write that down here.
The question, 3 times 10 power x
Yeah.
is where?
That is the C in this formula. C is equal to 3 times 10 8 meters per second. It is the speed of light. Yeah? Okay, can I continue? Yep. Right. Now, you have your answer for this binding energy, but how much is this per nucleon? So if I go back here, how many nucleons do I have? No, not nucleus. Nucleon is a proton or a neutron. So I have 4. Yeah. So how much do I have per nucleon? That would equal this number divided by 4. So what is that here, please? Well, it's going to be about 1.12. Yes. But if I do it to 2 decimal places, 1114. 1114? 114? No. Are you sure, Hugh? Abraham, check on the calculator and settle this for us. it's okay. It's okay. It's not a problem. Times 10 to the minus 12 joules per nucleon per each element, each proton neutron. Now the reason I'm talking about this is because I want to show you a graph now. So we got our answer, it's 1.11 times 10 to the whatever. Again, that should say HE. So this is an interesting graph here. This here is the mass number. So for example, in the helium, what's the mass number? It was 4. The mass number is 4. So that will have it down here. And this is how much energy is required per nucleon. The unit here is mega electron volts, but that's not too important right now. So what happens is, as the atom gets bigger, you actually need more energy per proton and neutron. But then something interesting happens after here. You need less energy per proton and neutron to hold the atom together. So in fact here, around about iron, this is the most stable atom. It's the one with the strongest, biggest, most powerful bonds between the protons and the neutrons. So it's very difficult to separate this because you have the most per proton neutron. Okay? And this is the graph is binding energy per nucleon. Now there's lots of information on this graph, that's not important. What's really important for the exam, because they may ask you to draw this, it's on the syllabus. This is what you would need to draw on the exam. Here would be the mass number, and here is the energy per nucleon, and this could be in joules, doesn't matter. And the graph looks like this. And right here, no, because you always need some energy to bind. Like I think the smallest one is like hydrogen 2, 1 hydrogen and 1 neutron. So this I think is the smallest one. This here is iron. What number is iron? Is like, what's iron actually? I think the mass number for iron is about 60. The mass number. Do you know how many protons? No? Alright, well I think it's about 60, I'm not sure. Actually maybe it says it here. Oh, there, 58. So that's what you might need to do for the exam. So as the atoms get bigger and bigger, there's less binding energy per proton-neutron. This makes them easier to separate. In fact, I think down here you're going to have something like uranium, yeah. Here would be something like uranium, and here would be iron. And what would be here, down in the kind of 1, 2, 3 area, here you would have things like hydrogen and helium and stuff like this. Yeah. I don't know. This you haven't done in chemistry, right? Yeah. So this one here, it's quite easy to separate the bonds here because it's smaller. Okay, can I go back now to the slides? Yep. Okay, now I have some questions here. I know it seems like a lot. So in the first one here is how much energy do you need to balance this? So you've got a hydrogen 2, it makes a helium 3 and a neutron, and we want the energy here. And then we have another equation. This is, sorry, that 5 should be up the top here, I'll fix it, that should be 235. A uranium plus a neutron, and then they go together and they will make a barium, a krypton, 3 neutrons and some energy. What's the energy here? What is the energy? How many moles are in 1 gram of uranium? How many uranium nuclei are in 1 gram? So that relates to that. How many reactions can be produced using 1 gram? How much energy in total can be produced? And then there's a question here about power. And then here's one about mass defect. Copper 63 is this. What is the mass defect? What is the binding energy? What is the binding energy per nucleon? And here's all the information you need. So it should be 235. So let me just fix that now before you do it. 2, 3, there's the problem right there. And then, what was the other problem? Like hydrogen. This should be helium. This should be helium. This should be helium. This should be helium. This should be helium, and it is. Okay. And lastly, neutron. That should be helium. Okay, 6. So I'll just open this again. Now you get these questions on the exam, and I hope you don't find them difficult because they're quite short. You know, in fact you're only using one formula. What formula are you using? E equals mc squared. And that's it for all of these questions. Okay. That is fixed. Right. So I don't think although it looks like a lot, I don't think there'll be a lot. Like for example, this one here should take you 2 minutes, 5 minutes, 2 minutes. So I actually think 10 minutes is enough time for this. So we'll give you 10 minutes to do it, and then we will look at the next lecture. Okay?